Okay, today we're going to work on some basics of exponents and how they kind of just work, I guess is the best way to do it. Here we're going to start with a little discussion of exponents and what are they, and the sort of an old puzzle or story or fable of how they work. And I've got these square-ish things lined up to be sort of a chess or checkerboard. I didn't usually, you got every other one of them, either black or red, or so it either goes black, white, black, white, or red, black, just depending on what you have. All kinds of different colors, all sorts of pretty ways to arrange it. But it's 8 squares along the top, and there would be 8 of them down, or 8 columns and 8 rows, for a total of 64 squares. 64 squares. At this time, I'm just doing 2 of them because it would take a long time to go through, and we don't want to do all that extra work. We're going to try and be smart, because that seems like a good idea. Anyway, the story goes, there was a king some time ago in the land of kings who had this very vexing problem, and he couldn't figure it out, and he'd asked all his wise men and all the wise women and sought for a solution to this problem, and he just couldn't find the answer. And finally one day a traveler came in, and this traveler had a deep and keen interest in mathematics on the side, but also was just wise in the ways of the world, and was able to solve the king's problem. And the king was so very happy. He was so very happy. He said, oh man, I can go to sleep at night, and now I can get back to ruling justly and properly, and I can eat well, and just be happy. Thank you. So in payment, you can take anything you want from my castle. And the traveler said, here's what I'll do. And he took out of his little pouch, traveling pouch, 1 grain of rice. 1 grain of rice. He put it on the square of a chessboard that was sitting before the king, because the king liked to play games in his free time usually. And now he's going to get back to it. So I said, now tomorrow you're going to put 2 grains of rice. 1, 2. Like so. And the day after that, you're going to double it. So on the following day, you'll put 1, 2, 3, 4. And you're going to keep doubling that amount of rice on the squares until the very last and 64th square, and on that day I shall return to collect my payment. The king, who was the king, so he didn't really need to know mathematics, he had people to do it for him, thought this was not a bad idea at all. It would seem like a pretty cheap payment. He was the king. He had all the rice he could ever imagine. A few grains of rice. And so we're going to see what happens on that 64th day. We're going to try and use a little bit of math and add in some things that may or may not have been written in the manner that we're going to do it now. So on the first day, there was 1 grain of rice. Well, we'll learn later on a different way to write it, but there was 1. And then it's times 2. So times 2. And then, actually I put a dot right here, times 2 again. So it would be 2 times 2. It would be 1 times 2 times 2, but the 1's not really going to come into play. And then on the third day, it would be 2 times 2 times 2. That's the 4th day. And then on the 5th day, the 5th square, this is getting cumbersome to write. We're going to rewrite this in a short form with a base of 2, an exponent. That's the exponent of 4. That's 2 times itself 4 times. The following day, 2 to the 5, 2 to the 6, and this will be 2 to the 7. Now this is just 2, 4, 8, 16, 32, 64, 128, 256, 256 here just goes, 256, 512, still not much rice, it's a bag of rice, 1024, was it 2048, popular game, 5096, but this is going to get hard to keep multiplying this in my head, so I'm just going to go back to what I was doing before. 2 to the 8, 2 to the 9, 2 to the 10, 2 to the 11, 2 to the 12, 2 to the 13, 2 to the 14, 2 to the 15. Now, we're going to keep doing this all the way down to the 63rd square. Notice how on the second square, so the second square is 2 to the 1, so 1 times 2 times 2 times 2. This is the second square, the third square, the fourth square. We can rewrite this as 2 squared, 2 to the third. And we'll just keep on going to the final 2. And this would be 2 to the 63rd times 7 to the 63rd. I'm feeling a little lazy, so I entered it in the calculator. And it came out to be, let's see, what does that say? That is 9.22 times 10 to the 18 is what the calculator said. It actually used a different notation kind of, but that's what it said. Because this number is so huge. That says this would be moved over 18 times. We've written it out of standard form. So 9, 2, 2, then we're going to have what, 16 zeros? So 1, 2, 3, 4, 5, 6. We'll put some commas there because that might help us see what we're doing. You know, remember after every 3 we have commas. And so we got and we got our thousands, millions, billions, trillions, quadrillions, 9 quintillion. 9 quintillion. There is not that many grains of sand on the entire planet, much less grains of rice in this king's kingdom. And he had to default on his debt. He couldn't pay it. He couldn't even get anywhere near this, because when the traveler came back, he said, "Where's my rice?" He said, "No, I'm sorry, I gathered everything up, but I couldn't do it." And there was already these mounds and mounds and mounds of rice, far more than one can eat. And that was the story. Some versions have the traveler inheriting the kingdom. Probably not what would happen, but sure, why not? Anyway, that's an example of an exponent at work, and here it's in a myth or a riddle or a story or a fable or what have you. But that's one example, and they are used in all aspects of life, all manner of places. So understanding them is really quite useful. We start with, let's make sure I got it. We start with a base. So that's any number or something that represents a number, and then its exponent. So we have like 3 to the 4th. 3 to the 4th, the bottom number of the base, that's the exponent. 3 times 3 times 3 times 3, which is 81. This version has all kinds of useful sort of shortcuts and properties we can use with it. This is the long way, and this is the number that we know it to be, that we don't always have this output number. We might have something like x to the 4th, and x at this moment was representing something. So we can't know anything but this x times x times x. So it's really the easiest thing to do is write it as x to the 4th. Down the road, if we need to know exactly what x is, for that scenario we can figure it out. But we're just working on the properties of the exponents and how they work. Now we're going to look at tens for a second. Tens are useful to examine some of the trickier first concepts that we have, because our system is base 10, which means we work with tens, and that comes from the fact that we have 10 fingers. We just have a more natural understanding with tens. I'm going to look at this. 10 to the 1 is 10. 1 with 1 0. 10 to the 2 is 100. 10 times 10. 1 with 2 zeros. 10 to the 3 is 10 times 10 times 10, or 1 with 3 zeros. We could go on this way forever and ever and ever. 10 to the 100 would be Google, or 1 with 100 zeros. We're going to go the other direction though. What about 10 to the 0? And we follow this pattern. We got 10 to the 3 has 3 zeros, 10 to the 2 has 2 zeros, 10 to the 1 has 1 0. So 10 to the 0 would be 1 with no zeros. But something to the 0, or part of our logic tells us that it should just be 0 because it doesn't show up any times, and that just doesn't seem to make sense. So let's look at it in another way. I'm going to say that, let's see, start with 10 to the third, and then we'll work backwards. 10 to the third is 10 times 10 times 10. We can also write that, see how it is 10 to the 10 times 10. We can also write that as 10 squared times 10, or 10 to the 1. We can write exponents in all kinds of different ways, or numbers if the bases are the same. And we see how it's the one prior times 10. And we know that to be 1,000. So if we do 10 squared, it would be the one prior, which would be 10 to the 1 times 10. And that gives us 100, and all is looking good. We're following everything we know and understand. So yay, happiness. And then we got 10 to the 1. 10 to the 1 would be the one prior, which would be 10 to the 0 times 10. We know that 10 to the 1 is 10. 10 to the 0 times 10. So what number, keep going sort of up this way, what number times 10 is equal to 10? Well, that has to be 1. The question mark has to be 1. We could do algebra, we could do all kinds of things, whatever, we just know that the number times another number is the original number itself has got to be 1, or however you want to say it. That's just what multiplying by 1 does. So that's what we get. It's 1. Interesting. Now let's look at it with a few other numbers. See if that holds true. Didn't quite get all of it. I mean, what about maybe like a different color? 5 to the 0. Well, 5 to the 1 is 5 to the 0 times 5. We follow the same logic as before. Remember, 5 squared would be 5 to the 1 prior, times 5. And that's 25. We know that 5 to the 1 is 5, because it's just 5 one time. And so we have the same situation. What number times 5 is 5? So 5 to the 0, therefore, must be 1. Kind of strange. It is. But the answer is actually quite simple when we speak about an answer. Any number to the 0 is 1. So 3 to the 0, 1. Negative 27 to the 0 is 1. X to the 0 is 1. There is only one spot where things get a little hazy. That's 0 to the 0. But to make it hold true, they generally just say that that's 1. It doesn't quite make a whole lot of sense. There's other ways to look at it, but just in general, it makes life a little easier. But so any number to the 0 power, the square root of 3 to the 0. 1. 1/2 to the 0 is 1. So in fact, this property makes life pretty easy. If you have something to the 0, you already know that it is just 1. We made our life a whole lot easier, see? We shall continue on our merry road, if I can get this to do what I need it to do. Third tries the charm. So we get down to 0, and usually on the other side of the number line after the zeros is a negative. So it wasn't until the past few hundred years in mathematical history that we had negatives. Oh, still in blue. We should keep consistency on color there. do 10 to the minus 1. Let's look over here. Each time I move, I either have fewer zeros, or the other way to look at it is the decimal moves. Remember the decimal here, and when I went to 2, it moved there, and there, and there. First, as we get down, so the decimal is finally right here at the end. See how that decimal is moving? Well, from here to here, go here. You move that decimal over one spot to 0.1. And now we can see it. Decimal moved over, got 1. Decimal moved over, got 10. Decimal moved over, got 100. Decimal moved over, got 1,000, and so forth. So we got 0.1. I can rewrite 0.1 as 1 over 10 to the 1. Doesn't really matter when you're talking about decimals, but this may work later on. 10 to the negative 2. I'm going to move that decimal over again, so 0.01 or 1/100th. 1/100 or 1 over 10 squared. Negative 3. 3.001, because we moved the decimal over one more, or 1 over 10 to the third, or 1/1000. And we could keep going like that forever and ever and ever. We won't, because we see the pattern, we've shown it, we've demonstrated, we understand it, we'll go with it. We've decided it'll work. But we'll look and see how it works with numbers that aren't 10. That aren't quite so, don't seem quite so nice and easy. And so we'll try maybe 3 to the negative 2. Now if you look back on it, I think I had like 10 to the negative, we'll do 10 to the negative 4. That would be 1 over 1, 2, 3, 4, or 1 over 10 to the 4th. What we're going to do, and I could explain this in a different way, but we'll stay kind of simple here, is we're going to say, well, the exponent just seems to move it to the other side of this fraction bar, or the negative side. And so we can rewrite this 3 to the negative 2 as 1 over 3 squared, or 1 over 9. And maybe 4 to the negative third would be 1 over, and the 4 is still going to be there, but if we rewrite it down here, it's 3. Notice one nice thing about the negative exponent is it took something that could have been a messy decimal or a messy fraction, 1 over 64, and turned it into neither a fraction nor a decimal, just a number of the base and an exponent. So like if we have x to the negative 5th, that could be the same as 1 over x to the 5th. This looks a lot more cumbersome to work with, and oftentimes is. Here, not so bad. And we'll find other reasons that it makes more sense to do so. We'll take this a little step further. One more step. And look at sort of fractions as a whole with an exponent. Not anything too tricky. So like, let's say I have, first off I'm going to do like 1/2 to the negative 2. The negative, what it really did was flipped it over. So this now becomes 2 over 1 to the 2. And we can sort of look at it, this says, well, it's 2 squared and 1 squared. So 2 squared and 1 squared, or just 4 over 1. All different ways to write the same thing. That's a very large part of what we do in algebra, just reorganizing things. So it's not nearly so complicated as it looks though. So if I have 2/3 to the negative third, they can be rewritten. So the negative says to flip it over, and we can either keep the exponent up here, or sometimes in some of your exercises you'll be asked to sort of multiply it out, 3 to the third and 2 to the third, and all is good. You can do the same thing. You can also be given a problem where you have maybe 1 over x to the 6. And you want to write that as a positive x, or without having a fraction. What we can do is we can bring it up by changing the sign, x to the negative 6. Or even 1 over x to the negative 4th. I can bring that up by changing the sign. So therefore we've got an idea of what basic exponents are, the 0 and the negatives. I hope you've learned something, and then it's time to have fun or study up on your math and bottom, or just learn a great deal and have a good day.